Okay. We'll start with the phenols today. Now, aromatic alcohols. Okay. Now, this means that in the case of phenols, there is an aromatic ring to which an OH is attached. Okay. So, if I'm talking about an aromatic alcohol, it is going to be a benzene ring, okay, to which an O and an H is attached. Now, this is what we call as phenol, also called as carbonic acid. Okay. It is also called as C6H5 and an OH. Okay. Now you see the carbon to which the O is attached is actually an sp2 hybridized carbon atom. Why? Because this carbon is bearing a double bond. So whenever there is a double bond, the carbon is having an sp2 hybridization. So obviously the bond length between carbon and oxygen is going to be smaller or less. And therefore the rupture of the carbon and oxygen bond in this case becomes little difficult compared to when you see it in the case of aliphatic alcohols. Okay. Another very important that we have to understand in the case of aromatic alcohols is that the aromatic alcohol, if I look at the structure of the aromatic alcohol, then what we find is that because of the double bond, and this is oxygen, this is an H, and this has lone pair of electrons. So since this part of the molecule is an highly unsaturated system, it is going to pull the electrons towards itself. All right. So this oxygen, because it has a lone pair of electron, it will give this, and therefore a partial double bond character will also be established. What happens in this entire process is, because this part of the molecule is electron withdrawing, all right, because it is an unsaturated system, it is withdrawing electrons. So what happens is the removal of hydrogen as an H plus becomes easier. Any compound, when it can give hydrogen as an H plus, is considered to be an acid. Now, the same thing we had also studied in the case of aliphatic alcohols, that when the oxygen hydrogen bond ruptures, it is acidic. It is showing acidic nature. Would classify them in the basic having a basic nature, but the entire, like I have also mentioned, that the entire organic chemistry, when you deal with compounds, it's a relative status. Here also the phenols are H plus. But what we understand is that in the case of the aromatic alcohol, since the electrons are being withdrawn by the unsaturated ring, the removal of H plus becomes easier, and therefore the phenols are considered to be more acidic than their aliphatic alcohols. All right. In the aliphatic alcohols, you saw that the primary is the most acidic, then is the secondary, tertiary. Why did the acidic strength of tertiary decrease? Because the carbon which is containing the OH is attached to 3 alkyl groups, and these methyl groups, being electron pumping, are showing a plus I effect towards the carbon, stabilizing the carbocation that may be formed, and therefore the acidic strength in this, we have to talk about the rupture of this bond here. So you see, these electrons are being moved towards, okay, these electrons are being moved towards oxygen, and therefore strengthening the negative charge on oxygen, and therefore the removal of H plus becomes difficult. All right. Therefore, the tertiary alcohols are least acidic, whereas the primary is more acidic. However, the phenols are considered to be more acidic than the alcohols due to the resonance stabilization of the phenoxide ion. Now, what is a phenoxide ion? Why is it resonance stabilized? To understand that, let us come to this part again, that in the of a phenol, once the phenoxide ion has been formed, the resonance stabilization occurs due to this technique. I'm keeping this molecule here and we'll do the resonance stabilization, the different resonance structures. So after this hydrogen leaves, all right, the compound getting is going to be like this. Draw the bonds here. So these are the 3 bonds on the benzene ring. And after the hydrogen has left as an H plus, it is left with an O minus. This is actually having, if I show the electrons in blue, it is actually having one, or you can say 3 pairs of electrons on oxygen. This is carrying a negative charge, you see, because now this is being given to this oxygen carbon bond, then the next resultant structure that we see is going to be like this. You have a benzene ring, okay? You have a benzene ring, and in this case, since the electrons have moved to this part I am discussing, the electrons move to this carbon here, okay, then what is happening is that these electrons will move here, because a structure, what you see is you actually get an oxygen with a double bond, okay, and these remain intact. And there is the difference. The difference is that the negative charge. Okay, the negative charge which was on the oxygen here, okay, has come to here. And similarly, this electronic movement within the molecule will continue, and whereby when this carbon gets here, this carbon here, when it gets a negative charge, it induces this carbon to form a double bond. So in the next structure, what you are going to get is, what you get is that the oxygen is doubly bonded with 2 lone pair of electrons, okay? 1 lone pair has been given to the system. Here it forms the double bond, and the negative charge is actually going here. All right, the negative charge actually goes here, and you see this has now become negatively charged. And similarly, it will also move to the next position. And therefore, what you get is the oxygen, which is doubly bonded here again, is having the electronic movement is such that it is having a negative charge here also. All the 3 are not occurring simultaneously, mind you. One negative charge is finding 4 places to reside in. Either it is going to be on or it will be on the the carbon. Now, when this is happening, when this kind of a resonance stabilization is occurring, there is a delocalization of the negative charge from the oxygen towards the you understand what is delocalization? The negative towards the benzene ring. All right. And therefore, what happens is this ion is called as the phenoxide ion, and this phenoxide ion is gaining stability due to the resonance phenomena that is occurring. Hence, we say that resonance stabilization of phenoxide ion is seen in this case, and that is why the phenols are more acidic than the aliphatic alcohols, or you can say alcohols. Now you see one more here. In the case of aliphatic alcohols, we were talking in terms of minus I and plus I effect. Okay. If there is an increased plus I effect, obviously the acidic behavior was decreasing. But here what is happening? Here it is the minus I effect. Why? Because the electrons are being withdrawn from the oxygen, and therefore it is making the removal of hydrogen as an H plus more easy. So it is a resonance stabilized phenoxide ion. So keeping these properties of phenol in mind, we will do the study of phenols according to the reduced syllabus that we have to follow. Okay. So the first thing that we will do here is, of course, the rest of the things you know that it is a cyclic compound. Each carbon atom is sp hybridized, sp2 hybridized, and the benzene ring has each carbon atom is attached to 1 more hydrogen, and so on. Okay. So now let's go to the methods of preparation of phenol. So we are going to do methods of preparation of phenol. Now, in the methods of preparation of phenol, uh, of phenol, you have to do, I think, 4 methods. One of them is the manufacture also. Okay. The first one is from benzene diazonium salts. The first method that you have to do is from benzene diazonium salts. Now, when you are studying organic chemistry, especially aromatic compounds, you must know what a benzene diazonium salt is. Okay. Diazo word, whenever it is there, no, it is indicating that there is nitrogen bond. Okay, so this compound is actually benzene. There is a triple bond between the nitrogen, and there is going to be a Cl minus. Okay, so this is the positive charge on the nitrogen, and the chlorine has the negative charge. This is benzene diazonium chloride because there is a chlorine ion attached to it. Okay, this will very readily undergo hydrolysis. All right, so plus H2O if you are taking, all right, in presence of an acidic medium, and you warm it. Okay, and you warm it. It will undergo hydrolysis reaction, and very simple to remember because the N triple bond N is going to form. I can show the circle or I can show the bonds. It's okay. And this is going to take an OH plus an N2 will be formed plus an HCl will be formed. This is a very simple, easy method to remember in preparation of phenol from benzene diazonium chloride. Okay. How is benzene diazonium chloride prepared? It is prepared by treating benzene with nitrous acid and keeping the temperatures very, less than 0 degree. So those conditions have to be applied. But right now, since it says how to prepare phenol from benzene diazonium chloride, we already have benzene diazonium chloride, and we are going to prepare it by the hydrolysis reaction. The second method that you have to do is from benzene sulfonic acid. Okay. Now, what is a benzene sulfonic acid? See, this is a benzene sulfonic. Okay. Okay. It's going to have an H. So if it has an H, it's going to be benzene sulfonic acid. But if I'm writing an N here, it is sodium benzene sulfonate. All right. It comes from the benzene sulfonic acid. This is then treated with NaOH. Okay. You treat this with an NaOH, and when it is fused or the temperature is kept around 600 Kelvin, and the reaction is made to undergo under these conditions, then what you are going to get is actually a sodium phenoxide. All right. This, when it is treated with HCl, it is going to form the phenol. That is the desired product, and you are going to get a phenol here, and minus NaCl. Okay, actually here also, due to the fusion reaction, or here you have to actually use 2 molecules of NaOH when Na2SO3 will be given out. All right, so this you have to keep in mind, that is Na2SO3 will be given out. So this is another method. Okay, this is from sodium benzene sulfonate. Sodium benzene sulfonate. All right. The third method, which is again a very important method, is the Dow's method. The Dow's method for preparing. I'll go to the next page to explain this. Okay. Dow's method. Now, in the Dow's method, the reagent used is chlorobenzene. All right, it's a chlorobenzene. This is again treated with a base, that is 2NaOH. We actually want to introduce an OH group. So you see the base has to be used here. And then this, under high temperature and pressure, you can write, or you can exactly mention the temperature. That is going to be, okay, this is actually 623 Kelvin. Okay, and 320 atmospheric pressure, or you can increase the pressure, just write high temperature and high pressure. Okay, and this is going to form a sodium phenoxide, again, which upon distillation with HCl, or when it is treated with HCl, it will give the phenol. So this is what you get here. Now, how is this process actually occurring. If you see, it is a two-step method. In the first step, what is happening is that if this is the chlorobenzene that we are talking about, we have taken this chlorobenzene, like I told you, okay, like I told you that each of these carbon atoms are having a hydrogen also. Okay, so I'll keep this bond here like this, and this is here, and this is having a hydrogen. In fact, all the carbon atoms are having a hydrogen. I'm concentrating on only one of the hydrogens here. What will happen is that in presence of a base, this is the first step that is actually occurring. So in presence of an OH minus, this is actually going to be removed. Okay, so you will get, what you are going to get is, a Cl, all right. And since hydrogen is moving out as an H plus, a negative charge will be left here. All right. This negative charge will be left here. And in the next step, what happens is that the chloride ion leaves. And like this, then what is happening here is this, there should be a bond here also. So what is happening here is a benzene is obtained. So this is going to be like this, and triple bond is formed here. This is the benzene. This is the benzene that is formed. Okay. And in the next step, that is the second step, what happens is, in the second step, what happens is that the benzene now undergoes hydrolysis. Okay. So you have the triple bond here. This is now going to add up an OH minus, all right, and it's going to add up here. So in the next step, what you will get is a formation of a OH, all right, OH adds up, and still there is a negative charge here because this electron has moved here. So there is a negative charge here, and this then in presence of an H plus is going to be neutralized, and what you will get is an phenol. This H plus will be picked up by the oxygen. Okay, this has to be here. And you will get a phenol. Okay, it gets a little congested to write here. All right, so these are the two steps that are formed. So it actually proceeds via the formation of a benzene, and then the benzene undergoes hydrolysis to form the phenol molecule. So this was just two steps that are in about the Dow's process that you are supposed to know. Again, in the board exams, they don't ask you for mechanisms unless they have mentioned the reaction's name. But sometimes, they ask you that how does the Dow's process proceed? What is the intermediate that is formed in the Dow's process? So at least you can mention that. Okay. And the next one, that is the fourth one that we have to do, is preparation of phenol. Actually, it's a manufacture of phenol from cumin. Okay. Now, what is cumin? From cumin, if I write, okay, then what is this compound? This is actually, see, what happens is you treat benzene with a propene molecule. Okay, CH3CH double bond CH2. And this is treated in presence of H3PO4 and high pressure. Okay, pressure and the temperature is also high, something around 520 Kelvin. Okay, when this is happening, actually the addition of the benzene group happens at the middle carbon atom according to the Markovnikov's addition only, you can say, because see there is one hydrogen. All these carbons are having one hydrogen. So one of the hydrogen, all right, the bond is going to rupture from here under pressure and the reaction conditions, and what you will get is a compound which is going to attach. Okay, either you show the ring or the bonds, it's okay. So this carbon attaches itself here. There is one hydrogen. The hydrogen that was on this carbon atom, the hydrogen that was there on this carbon atom goes to this and forms a CH3, and this forms a CH3. This compound is called as cumin. This compound is called as cumin. It is also called as 2-phenyl. It is also called as 2-phenyl propanone. Propane. 2-phenyl propane. You see, this is the IUPAC name of the compound, or you can also call it as isopropyl benzene. Isopropyl benzene. Now look at the names. This is the IUPAC nomenclature. So when it is IUPAC nomenclature, you will select the straight chain which is the longest. Obviously, it's a propane molecule to which the phenyl is attached. So alkyl groups, phenyl groups are considered to be the attachment substituents. So they don't go into the parent name. So this is going to be 2-phenyl propane. And the common name can also be isopropyl benzene. Why isopropyl? Because the propyl group is adding through the middle carbon atom. Okay. So this was just the preparation of cumin that I explained. In the next step, you have to do how phenol is going to be obtained from this. So you have a CH3 and a CH3. This is the cumin, isopropyl benzene. This is actually subjected to aerial oxidation. This is subjected to aerial oxidation around 368 Kelvin. It is treated when a peroxide of this compound is formed. Okay, and when a peroxide is formed, you know it is supposed to have oxygen linkage, and it is going to be like this. The rest of the two CH3 groups will remain as they are. Okay, it is in the next step that when it is treated with dilute HCl, you get a molecule of phenol, all right, and acetone is obtained. That is why this reaction is important, because you have to do acetone also. So if I start with cumin, then I'm getting two compounds. One is the acetone, and the other one that I'm getting is a phenol. Even acetone is prepared on large scale by this method. All right. Okay. Next is, now phenol is a colorless, crystalline, deliquescent solid and has a melting point of about 42 degrees Celsius. In the labs also, you will see that when phenol, is kept in a bottle for some time, instead of showing a colorless color, it changes to slightly pink on exposure to air. All right. Air and light, in the transparent bottles also, you can see that it is turning to that color because part of it is getting oxidized. All right. And phenols are not very soluble in water. So that is why you can actually see, if you add water to it, you can actually see the two of them, not mixing. They form a heterogeneous mixture. All right. So now coming to the chemical properties, very quickly, I'll try to complete this part here. That is the chemical properties of phenol. Since we have already explained the acidic nature, we will quickly do for the phenol. We'll do the reactions quickly. Now, if I look into the syllabus, the reactions are given. I think the reactions that are mentioned are, you have to do with sodium, with zinc, with RCOCl, with acetic anhydride. So you have to do reactions with sodium, you have to do reaction with zinc, you have to do reactions with acetyl chloride, that is CH3COCl. You have to do reactions with CH3, C double bond O. Okay, that is an acetic anhydride. Then you have to do reactions with PCl5, and you have to do reactions of bromination, nitration, and sulfonation. And of course, two other special reactions you have to do, that are the Kolbe's reaction and the Riemer-Tiemann reaction. So first we'll try to complete these reactions. Okay, very quickly we'll just write the reactions. Now see, phenol. I will write the phenol group here like this. Okay, OH. All right, now let me do this. With sodium, all right, two atoms of sodium, if you are taking, it is going to form sodium phenoxide, ONa. Okay, and hydrogen is released. So it is an acidic nature because it is giving out hydrogen in this case. All right. Similarly, in the next case, if phenol is acidic, will it react with NaOH? Let us try it out. Now, NaOH is a strong alkali. Hence, it reacts with phenol, which is weakly acidic, and NaOH is a strong alkali. So it gives the above reaction again to form sodium phenoxide, and it is going to give H2O and not hydrogen. It's going to form water. So salt and water are formed. So kind of neutralization reaction is occurring. But phenol does not react with weak alkalis like sodium carbonate or sodium bicarbonate, because it does not have that much of strength, acidic strength, to react with weak alkalis. Then the next reaction that we have to do is with zinc. All right. Now, what happens is that if we have to try out the reaction with zinc, then remember zinc behaves a little differently, though it is a metal, but it reacts with active metals to liberate hydrogen. But when it is treated with zinc and heated, all right, then it forms benzene. Then it is reduced to benzene. Children, this is again very important to remember, because it is acidic nature and it is a metal that we are using, so it is going to liberate a hydrogen. No, it doesn't happen. It is actually going to form zinc oxide and form the benzene. All right. Then what is it going to form? We'll go to the next. Okay, let me do ammonia here. When it is made to react with ammonia in presence of anhydrous zinc chloride. All right, zinc chloride is used, which is anhydrous. All right, anhydrous. And of course, it is heated. And when it is heated, then in this case, it is going to form an amine. That is a primary amine. All right, so what you are going to get is an NH2 will be attached. So I have just rotated the molecule a little bit. So the NH2 has come on the side and it's going to form an H2O. All right, so these are very easy reactions to remember, but they are all different from each other. You can check that. With the active metals, it's going to form the phenoxide salt and liberate hydrogen. With sodium hydroxide, that's a strong alkali, it forms salt and water. With zinc, which is a moderately reactive, for that it is going to form benzene and zinc oxide. And with ammonia, it is going to form NH2 attached to the benzene ring, that's an aniline, and it's going to form the H2O. Okay, so this is how it is going to react. Now the next is you have to see the reaction with acetyl chloride. All right, I'm just doing the reaction as you are supposed to do, in terms of the reactants and the reagents and the reaction conditions. So if this is CH3COCl, again, since we are discussing the acidic nature, you can understand that an HCl will be lost in this case in presence of pyridine. I have already told you earlier that pyridine is weakly alkaline, and therefore it takes care of the HCl that will be formed. And the compound that you are going to actually get here is, this is it. You get this compound is called as phenyl acetate. It is methyl phenyl ester. You see, it is methyl phenyl ester. And since this is the chain, this is the carbonyl group is attached to CH3 here. That is why the name is going to be phenyl acetate. All right. I hope you know the difference between phenyl acetate and methyl phenyl, when the benzene ring is going to form the ester ion. Okay. Now the next is reaction with acetic anhydride. Again, in this case, only if I write acetic anhydride, you can write acetic anhydride like this also. Okay, so it is CH3C double bond O. Now this is going to rupture from here. All right, and when it ruptures from here in presence of an H plus, so one of the molecules is going to form the acid and the other molecule is going to connect with the phenyl group. So the compound that you get in this case is going to be an OCOCH3, just like you got here in the previous case. And of course, an acid molecule will be formed along with this. So this is the acetic acid that you will get with this. Okay. The next reaction that you have to do is with PCl5. And we know that very easily. We know, I will take the PCl5 here only. PCl5, what happens? It is a very good reagent to replace the OH group. So actually you will get a chlorobenzene. You will get a chlorobenzene, that is a Cl, and of course a POCl3 is formed, and of course HCl will be given out. So this is the reaction with PCl5. Now the next set of reactions that we will do are the reactions of the benzene ring. Okay, now what happens in the case of benzene ring? This will take about 5 minutes to explain, and then after that we will do the mm, part. Now you see, in the case of benzene rings, we have something called as orthopara directors. Okay, remember that OH group is an orthopara director, or the groups can be meta directing. Now for the same reason, in the case of phenoxide ion, if you remember, the negative charge was created on the ortho and the para positions. Okay, now in this case what happens is, when we treat this with Br2, all right, when I treat this with bromine water, that is in aqueous, all right, 2 molecules of Br2, the phenol is going to add up, okay, at the ortho-para position, that is OH. The phenol is going to add up the bromine at the ortho-para position. Because OH is an orthopara director. Now you see any kind of reaction on the benzene ring. See, benzene ring is actually sandwiched between the electrons. So a negative reagent will not approach it. So what will approach? Definitely a positive reagent, that's a nucleophile, will approach. Now when, an electrophile will approach. So electron loving reagents will approach. So what happens is that the bromine molecule is actually going to break up into Br plus and Br minus. Whatever the approach is, the bromine is going to add up at the ortho and the para positions to form 2,4,6 tribromophenol. All right, tribromophenol. Why is it forming a tribromophenol? Because all the three, that is the 2 ortho positions and 1 para positions, is being occupied by the Br. Which are the ortho positions? This is an ortho position, this is an ortho position, and this is the para position. Because all the three are occupied, this is the name is 2,4,6. Why will it be 2,4,6? Because the carbon which is attached to the OH is numbered 1. Now after this, whether you go in this direction and number it 2, 3, 4, 5 and 6, or whether you go in this direction, the numbering will be the same. That is, it is 2,4,6 tribromophenol, and a white precipitate is obtained. This precipitates, all right, it's a white precipitate. This experiment you also have to do it in the lab, okay, where we are very careful, the bromine water capsules are there, the files are there. It has to be, handled very carefully, otherwise it gives blisters. And a white precipitate of tribromophenol can be easily seen. All right. However, if you carry out the reaction in presence of carbon disulfide or CCl4, all right, that is, if you are carrying out the reaction in presence of carbon disulfide or carbon tetrachloride organic solvents, then in this case you can get both the products separately, that is ortho and para products can be obtained. So this is one important thing you have to remember about bromination. So what is the compound formed? It is 2,4,6 tribromophenol. However, make sure that on the arrow, whether any solvent is written or not. If the organic solvent is given, then of course it is going to form the ortho and the para product. Okay, the next is the nitration reaction. In the case of nitration reaction, if I take the phenol again, okay, in the case of nitration reaction, I'm going to treat this with HNO3, and if I'm taking the diluted form, OH, okay, then this is going to lose a water molecule and it is going to form either the ortho product or the para product. So the ortho product is going to be OH and this is going to be NO2. So this is ortho-nitrophenol. This is the ortho product, okay. This is the ortho product, ortho-nitrophenol. When you do hydrogen bonding, you talk about this compound to show intramolecular hydrogen bonding, if you can recollect. All right, and it also forms the para product, okay, where the nitro group will be on the para position. So this is about 40% and this is about less than 40% also. But if concentrated nitric acid is used, if we use concentrated nitric acid, that is HNO3, all right, in presence of H2SO4, where actually the nitronium ion will be generated, then the compound that is obtained is a trinitrophenol, which is also called as the picric acid. So you have all the groups, having all the three positions having the nitro compound, the nitro group, and therefore this compound is called as 2,4,6 trinitrophenol, or it is also called as picric acid. It is also called as picric acid. All right, in order to obtain high yield of picric acid, the phenol is first treated with sulfuric acid, and then a mixture of 2-phenol sulfonic acid and 4-phenol sulfonic acid is obtained. It is then treated with HNO3 to get the product. However, you don't have to go into the details of all that. Just know the products of nitration. Make sure what is written: dilute HNO3 or concentrated HNO3 and concentrated H2SO4. All right, benzene will not undergo nitration if this combination of concentrated nitric acid and sulfuric acid is not there. However, in phenol undergoes the reaction because with dilute HNO3 to form either the ortho or the, in fact, ortho and para products both will be obtained. The next is the sulfonation reaction, and in the sulfonation reaction, again, it is the sulfonic group which will be introduced, and quick reaction in this case, if you can understand, this is the OH. All right, then in the case of the sulfonation reaction, if I treat this with concentrated H2SO4, all right, concentrated H2SO4, because SO3H group has to be added up, concentrated H2SO4, all right, at 293 Kelvin, okay, then it is going to form this compound. It is going to form an OH, and an ortho product will be obtained, SO3H. All right. However, if the temperature is increased further, then if you increase the temperature further, I mean, if the temperature is higher than this, that is around 370 Kelvin, then it may form the para product. Okay. Then it is going to form the para product. Okay, so here you get the para product, SO3H. All right. So this is it. Now the two special Kolbe's reaction and the Riemer-Tiemann reaction. Again, mechanism you don't have to do. We'll just do two of these reactions and then that will complete the phenol. So Kolbe's reaction, just know the reaction. Very simple to understand and remember. Sodium phenoxide, if you are taking, again, sodium phenoxide can be obtained easily from phenol. So when this is treated with, okay, let us say NaOH, what you are going to get is a sodium phenoxide. So I will write the sodium phenoxide here like this. Then this at 400 Kelvin, all right, and at high pressure, not very high, but okay, high pressure, all right, it's going to form a compound which is OH and COONA. Acidic medium, it is going to form a compound. Why I am writing it like this is because this compound that is obtained is salicylic acid. All right, this is a very important compound. It's a salicylic acid. All right, this is Kolbe's reaction. So you start with the sodium phenoxide at high temperature and pressure. It's going to get converted to COONA. All right. Oh, sorry, one thing. We missed out writing the CO2 here. This has to react with CO2. Only then the compound will be formed. None of you pointed out from where did the CO come. So the CO2 is going to, all right, and so this is how you will get. The next is Riemer-Tiemann reaction. The next is the Riemer-Tiemann reaction that we have to do. Okay, so I think I will erase this and we'll go to the Riemer-Tiemann reaction. So when we go to Reamer time and reaction, again, you are going to take RTR. This is short form is RTR. All right. So Reamer time and reaction. Let us do this and then we'll end the class today. OH. Okay. This is made to react with CHCl3. Okay. Plus 3 NaOH. Okay. This is going to give us, when you heat it, it is going to give us a compound which is called as salicylaldehyde, OH and a CHO. Name of the compound is, that was salicylic acid. This is salicylaldehyde. Okay, this is salicylaldehyde. Okay, it's an important compound. And the reaction proceeds via the formation or the generation of a methyl carbene. Okay, let's see what I'm talking about. This CHCl3 in presence of an OH minus, okay, it is going to actually lose out the hydrogen and it's going to form CCl3 and it's going to have a negative charge here. All right, it has lost one hydrogen, so it has become an H2O. This is going to lose out a chlorine and as a chloride ion, so you get a minus chloride ion, and it is it is this reaction intermediate that is responsible for, initiating this reaction. All right, then this CCl2 is actually going to attack the benzene ring, and when it attacks the benzene ring, let us say this is the benzene ring. Okay, it is going to attach itself here, and it is Cl2, one Cl and one Cl. When this is subjected to hydrolysis, the Cl gets replaced by OH. So you get a compound which is going to be, this OH remains, and this is going to be having a carbon with 2 OH. Okay. And of course, there is a hydrogen there also. And then, of course, this is going to lose out on a water molecule. And what you are going to get is a phenol group. You will get OH and a CHO. Okay, so this is how the reaction is going to proceed. And there's actually going to be a rearrangement here. The hydrogen will attach itself to this, and this is how the salicylaldehyde is produced. In place of this, one more point. In place of this, if CCl4 is used, then the compound is going to be a salicylic acid. That you have to remember. Okay, and of course, the other products that are formed along with this are NaCl and water. Okay, so test for phenol is, you can test it with the neutral ferric chloride solution when it gives a violet colored compound, and that's a very good test for phenols. So I think I have exceeded the time also. So this is about phenols that we are doing, and tomorrow I have a class with you. What time you want the class? Tell me, children. What time would you want the class tomorrow? Anyone?
Miss evening.
Evening?
Miss
What
evening
time?
Miss.
My usual time, 6 o'clock?
Yes, Miss.
Okay, fine. The rest of you are okay with that? Harshit, okay?
Yes, miss.
So many of these children did not join today. I don't know why. The other girls also did not join. Don't know what happened. Anyway, so that's it. Okay, children, enough for today.
Thank you, miss.
Thank you, Miss.